Hello, everyone. We're back with another talk at Computer Vision Talks after a very long break. And today we have with us Harold. Harold is a PhD student at UCLA, and we're going to talk about his work, DesCo, which is learning object recognition with rich language descriptions. This work was a part of a challenge at CVPR 2023, and this is first time we're going to hear about a challenge and how they won it. So we'll be asking questions around that as well, if that interests you. So stay tuned. Over to you, Harold.
All right, thank you for a very nice introduction. Okay, so today I'm very happy to share so I'm Harold, I'm from UCLA, and I'm very happy to share our work. We call it DesCo, learning object recognition with rich language descriptions. And by the way, this picture is generated by DALL-E. So first I'll give some background on the motivation for developing this work. Okay, so in recent years, there's a class of model which we call them language-based recognition model, has been showing very strong performance for many core computer vision tasks. For example, the most famous model is from OpenAI, the GLIP model, which shows that if you have access to a lot of images paired with text, you can just train a very strong image classifier by training your model to try to align images with their corresponding captions. So it's a very simple but scalable pre-training task. And what you get in the end is a model that you can query by just providing the image and with a list of captions. And the model, and you usually carry in the original paper, you usually query it with a very simple prompt, like a photo of something, and with a very like a photo of guacamole, a type of food, or a photo of Boeing 717, a type of aircraft, and you get pretty accurate zero-shot performance there. Okay. Let me try to hide. I think the control bar is hiding. Let me see if I can. Okay, I'm hiding the control anyway. So following this direction, so GLIP does it for image classification. There are some other important computer vision tasks such as object detection or segmentation. So people apply the similar idea there. So the general gist is you can convert any fixed vocabulary task you already have, like you're predicting from a fixed vocabulary on ImageNet, or you're predicting the fixed 80 class, you're predicting from a fixed vocabulary of 80 classes on COCO. Now you all convert them into predicting the alignment between your image or image regions and text prompt. And because of that, you can actually you can utilize many web scale image text pairs for supervision. And at the test time, you can just specify what you want to detect with a text prompt. And so this is one of our prior work called GLIP, which does it for object detection. So originally, you have to train object detector on a fixed vocabulary data set. But now you can see after converting it into a more of a prompt-based detection task, now you can just write what you want to detect there. Say, like, you can do this very classical COCO detection by writing all the 80 classes into a prompt, and the model will try to find what's in the picture. And you can also do it with much larger vocabulary and much more diverse and rare words. Yeah, like windshield wiper, wheels, license plate, etc. You also do raccoon, pistols, even like you can give a sentence. There are some holes on the ground, and you can also do it for like because your pre-training data set now becomes a web scale, a web caption data. You can also generalize later to these rare domains like thermal images. And so similar idea has been applied to other similar tasks like a segmentation. So you can see that you can just say segment zebra, ostrich, water, etc., and the model will give you a very good segmentation. And also you can apply it to segmentation of parts. So the prompt becomes chair seat. You can even pair it with some image editing tools to create this chocolate chair. Okay, so that's the general background we are working in. So, but the next question many people are trying to ask is, can this model take more complex language queries? Okay, so why do we want to do that? The first is is that you hope you can with that you generalize better to novel categories by providing some common sense descriptions. Okay, so this helps achieve the goal of trying to do recognition in the wild, including like classification, detection, or segmentation in the wild. So on the right, I give you this example, a picture. And if I just say detect mallet, you may not know, like before I write this paper, I'm not 100% sure what a mallet is. But now if I tell you detect mallet, it's a kind of tool with a wooden handle with a round head used for pounding or hammering. So now you can, even if you don't know the word mallet, you can now guess what it might look like, right? So this helps make the task of generalizing to these novel categories much easier. And the second use case, which happens to be a challenge this year at CVPR, is that you can actually use it to specify your custom detection needs by giving like more detailed specifications. Say this is a box of donuts. Before this language-based recognition model, donut is usually not very widely available in your training data set, so you don't get good performance on this kind of a rare categories. But with like development like CLIP and GLIP, you might be able to like recognize, okay, this is a donut because your pre-training corpus has much richer semantics. But still, the model cannot support this. They call it like more of an instance detection. Say I want to detect the chocolate donut, or I want to detect the chocolate with the strawberry glaze, or I want to like detect the donut with shaped like a flower. That's not possible. So that's another area we think supporting more complex language queries will be useful. Of course, you can also imagine other scenarios what if you can do that. Okay, so you might think, okay, these models are pre-trained on image text data set, right? So naturally, they should be able to support this kind of a more complex language queries beyond entity names. So how do they do? So we did some experiments. So so the first example I'm showing is you are trying to generalize to this kind of a rare entity called eclair or tart, two kinds of sweets. And you give a description and you give it to the model. So the ideal case is because the show in the picture is eclair and not a tart, the model should not give any prediction for when I give the query of tart, but give a prediction for eclair. And you can see for the GLIP model, it basically just ignores the rich description I give it and just to say, oh, it's kind of food. So whenever you give me a food-like prompt, I will detect that food for you. So it's mistakenly treating this as a tart, which is not. But for our model, which I will introduce, actually you can do it pretty well. Yeah, and this is that mallet example I just gave. So this is even harder where we even hide out, we hide the entity names in the prompt. So I just tell the model, you're trying to look for a kind of tool. And in the first case, it's wooden handle with a round head. In the second case, it's long handle, but with sharp blade. And you can see for GLIP, it just tries to find tools for you. So it's predicting all over the place. But for our model, it can actually accurately know, okay, in the second case, even if there's a lot of tools in the image, but we're looking for a tool with sharp blade. So presumably we shouldn't detect that. Okay. Any question so far, or any confusion with the examples? Yeah, people have told me that this example is sometimes hard to digest.
No, it's pretty good introduction to prompt learning. Yeah.
Okay, thank you. Okay. Yeah. So another case is you are query with more of a natural caption or sentence, and people might think this is even easier because you are more closer to your pre-training distribution. But still, you can see the model exhibit is kind of a hallucination. Okay, the first caption is a clown making a balloon animal for pretty lady, and the second one is a clown kicking a soccer ball for pretty lady. So the first one is correct. So for So the model shouldn't give any prediction for the second one. But you can see the GLIP model, the model again ignores your language context and tries to detect the entity clown for you, regardless of whether this context surrounding clown is correct or not. So it actually somehow hallucinates a clown kicking a soccer ball, but it actually doesn't, there's no such thing. Okay, so we see some failure examples with our model. So this is an overview of what we're trying to achieve. Basically, we want to support more complex language queries with current models, and we're going to show why they actually fail at supporting this more complex language queries out of the box. Okay, so there's two challenges. The first challenge is the description I show you are very detailed and specific, and this actually can be very different from your pre-training data. So, so we want to have a way to actually scalably generate this kind of a detailed and specific language descriptions to use for pre-training. And second thing is, we find that even if you get your hands on a lot of this kind of a descriptive data, like the one you will see during inference, the model still may not actively make use of the information provided in the query without proper guidance. So that will be the second focus of the talk, is how can we force the model to actually read the descriptions. And with that, we have, we will combine it into our paradigm of we call it description conditioned learning, called DesCo. Okay, so any questions so far before I dive into the details?
No, we can do it.
Okay, great. Okay, oh yeah, here's another somehow like a sneak peek of what we're able to achieve. So these are like two, on the left is two very long-standing detection benchmarks. So if you're familiar with benchmarks, we can look at the scores. It's actually a very big improvement compared to those baselines. Specifically, like we take existing model GLIP Tiny and we add our description powered pre-training, and you can actually see that it sometimes outperform the larger model called GLIP Large. Yeah, in the LVIS case. Okay, and you can also see some example here that the model actually respond to your queries. So if you give it a so this is an inference time. If it to give you a if you give a query from a smaller GPT model, which is not perfect, says scarecrow is kind of object tall with a straw in its mouth. It's like it's not wrong, but it's not very very specific, right? And but in the Da Vinci case, if you give it a description generated by a larger language model, a more high quality one, you can actually successfully detect the object there. Okay. So so next I'll give some background on some prior work. So basically I want to introduce the baseline we use, which is the GLIP model we did about 2 years ago. So it's called grounded language image pre-training. So it's basically a generalization of the GLIP idea in a domain of object detection. Okay, so so what we want to do is the traditionally object detection is mainly treated as a classification task where you're just predicting from a fixed vocabulary. There we convert it into a language-based task where you write what you want to detect into a prompt, and the model will try to align regions in the image with words in your prompt. And that task actually is traditionally like known as more of a phrase grounding task, where you give a sentence and you're trying to ground the phrases into the caption to the image. So that's what we call it. With that formulation, you are unifying these two tasks of object detection and phrase grounding. And the benefit of doing that.
I have a question now. So the input or the prompt is basically composed of two parts. One is like the hard prompts like person, bicycle, and then also a phrase that contains those hard prompts.
It's yeah. So like it's more showing the model can support two types of prompts. You are not like every time you're not always giving the model two prompts. Actually, the model always just accept one prompt. It is just showing that there are various formats of prompt that you can use. Yeah, and this is the baseline GLIP model. Yeah.
Okay, understood. Thank you.
Yeah. So once you like write the detection into this format, so now you can train on both types of data there. You can train on detection data. You can also train on this kind of a phrase grounding data where your prompt is more of a natural caption instead of this concatenation of categories. Yeah. Okay. Yeah. So that, but that's not that's like the phrase grounding data. The annotated data is usually like you have a caption, but you also have boxes paired with phrases. So that's not very scalable. But so the power that the thing that actually give power to GLIP is you can actually now self-train on massive image text paired data. So so you get a lot of like millions of images paired with text on the web, but you don't have bounding boxes. But we find that after you train a model on gold phrase grounding data, you can use it to do inference on these image text pairs without any bounding boxes. And the model will give you a very accurate predictions there. So this is much more accurate than prior efforts in scaling up. So like the key data bottleneck in this kind of detection task is bounding boxes, because you are trying to locate stuff. And people have been trying to scale up the data of like trying to give bounding boxes to images, basically. But in prior work, this strategy doesn't work out very well, because you're usually just utilizing your pre-trained detector on images alone. So detector is in charge of looking at the image and determining what's in the image and also locate the objects. But in our case, we're doing more of a pseudo labels on grounding data. Basically, you have a guidance of captions which are given by humans you get for free on the internet that tells you what's in the image. So now your model has a much easier job of it doesn't have to determine what's in the image. All it has to do is I give you a caption, you just try to find the entities in the image for you. So that gives you much higher quality boxes than say I just give you an image without any captions and you have to find all the objects in the image on your own. Yeah. So that's the why we get much and more accurate boxes than traditional scale-up efforts. And we'll also cover much larger vocabulary, because in prior work, your model, you are using your pre-trained detector to predict on those images. So the vocabulary size doesn't change. But now you can actually like say, you can cover much more rich semantics using this kind of a data. Okay. So with that, basically the architecture is a model that takes an image paired with a prompt, and you can and then you can calculate the alignment score in the end between regions and your words, and you can so now you can do detection. And we further use that self-training idea to drastically scale up your data. So in the end, what you get is kind of a object detection or text grounding in the wild effect, that at inference time, you can just fit in whatever you want to detect. And because the pre-training covers a lot of data, hopefully you can get it right even in a zero-shot manner. So on the right, you can see some real examples of our model. Yeah, so and there's many great work along the line. I won't introduce them, but basically that's a similar idea where you can find a lot of image caption data on the web. You can find a way to give boxes or bit boxes or masks, segmentation masks to those data, and then you can train your model on them. So so that's a paradigm of the baseline. So what's the challenge here of trying to teach this model to understand more complex language queries? So the challenge one is very easy, like to see. So it's the kind of a fine-grained queries or descriptions that we want to feed the model at inference time may be rare in your pre-training data. This is because of the reporting bias, where in simple words is people don't write obvious things. So if you are given this image and you're asked to write a caption, your very natural instinct is just trying to say, oh, it's a toy bear holding a mallet. So we tend to directly use entity names rather than give descriptions of their subparts, shapes, and textures. So you actually don't get a lot of rich, detailed, descriptive data during pre-training. So our solution is also very simple. Is now you have very strong large language models. So you can actually just ask them to write the description for you. And we find they tend to be quite accurate. So just ask the GPT model, what are the useful features for identifying mallet? And the GPT-3 will tell you, okay, it's kind of tool wooden handle. Yeah, so the example I showed actually is from GPT. And you can sample descriptions for each noun phrase you find in your pre-training corpus, and this is fairly easy. And so that solves the problem. So now what you get is images and paired with your original caption. But from that caption, you can also extract some noun phrases and get description for them. So you also get a lot of paired descriptions from GPT-3, but with very rich details. So any questions so far?
No,
Okay.
none from
Yeah.
But just out of curiosity, using GPT-3, like it cannot be an online process, right? Like you cannot generate prompts and go with GPT-3, right?
Yeah. So like if you do it on the go, then you every time have to query. So that's very costly and slow. So we actually do is we like pre-build a vocabulary of the noun phrases. Yeah, on our pre-training corpus, and then you just sample for each noun phrase. You sample description, and you can control like which noun phrase you want to keep. Here we just keep the top 10K. Yeah. So So the solution one and the challenge one, number one, is seems very straightforward. But actually, after that, you might say, okay, can I just train a model on the data I just got by aligning the regions and their description, and the model should be able to generalize. Turns out you cannot. That doesn't work out of the box. So the reason is the model is not incentivized to read the descriptions. So it turns to learn some shortcuts that allows it to just ignore the descriptions. Okay. So the idea is because during pre-training, the objective is just trying to do a kind of a contrastive learning objective. You are trying to ask the model to align regions to your to the words. So you are trying to doing contrastive learning between regions and words. Okay. So in a sense, you are teaching, and usually you pack several queries or sub-queries into a long query. So usually what the model essentially is asked to do is to distinguish some sub-queries. So for example, if I give the model query 1 mallet, which has a wooden handle with a round head used for pounding or hammering, and question 2 axe, which has a long handle and a sharp blade, and ask the model which query aligns to the image. So this is a pre-training task. So you might find that you don't necessarily remember the descriptions if I ask a human to do it, because all you need to do is look at the entity name mallet and X, and you are able to align it to the image. So this creates a kind of entity shortcut that focusing on the center entity is enough to distinguish which query is correct. So the model is actually not incentivized to read the descriptions. Okay, so in a sense, once you give the once your image and the entity in your query is fixed, the region, the label of the region is fixed because the entity part is because the label of the region doesn't depend on your context. Yeah, so the model simply chooses to memorize the alignment between entities and regions and ignore all the non-entity part or non-center part. Okay, so this is very similar to the bag of word problem known in the vision like previously published. So it says that for GLIP models, it tends to ignore word order. So so if you give them, so this is a original caption, a brown cat looking at a gray dog and sitting in a white bathtub. And that paper says GLIP is just not sensitive to any word order switch you do. So even if like you just shuffle the sentence, a gray bathtub is looking at a white cat and sitting in a brown dog, or even like even more crazy swappings, the model doesn't distinguish them. They will give very similar alignment score and doesn't pick out which one is the most correct one from these shuffled sentences. So because this is similar observation to our that if you don't give enough incentives, the model is not will not pay attention to like description. In their case, it's the word order.
Can you go back to challenge 1? The challenge 2 is pretty interesting. I have a question for challenge 1. When you say the model ignores everything apart from the next slide, apart from the word axe and mallet, does it ignore everything after making an association that mallet is this, and the next time it is not considering anything apart from mallet, or it is just focusing on the first word? Because to identify the central entity, it would try to make correlations of the other words to the central entity, right?
Oh, I see. That's an interesting question. I think it can be like both. Yeah. So the first word is what has all the information that you need to identify what's what's in the image, and also like that also creates a bias that you usually like after you're training like in this way, the model will just say, okay, the first word is the most important. So every time just look at the first word. Yeah. Yeah, but this is more about but this is more of an artificial example. Like even you can just have more diverse ways of giving your descriptions, but as long like you can like you can put the word in the end or in the middle. But the idea is as long as that entity name give you enough information to identify what you want, then the model doesn't pay attention to your descriptions.
Okay, understood. Fair.
Okay. So how do we solve this? So this actually is very straightforward and simple. We try to create this Winograd-style query. So the Winograd challenge was a very long-standing style of challenge where you are given. It's originally for testing like language models, where you give the model two very similar sentences, but they differ only in very subtle and ways that require common sense reasoning. So so the model has to pick out which one is more plausible. So here we use a similar style that we try to create two queries that has the same type description. So we all say, okay, it's a type of tool. But then the subtle difference, the model has to read the fine prints to know which query is correct. Yes, it's basically trying to hide out the entity name, which will reveal like what's an entity we're looking for. But actually, just to give a more of a general description, general object name, but then give a description. So the model has to read the description. So the labels of the word tool now depends on its language context. Yeah, so the process is you're having the original training data. You can have a caption, or you can also have a detection data, which directly give you the label. So extract the entity from there, and you ask GPT-3 to first write description for that correct entity, but also give a confusable object and also give description. Then you throw out the actual entity name, and you just give these two confusing sentences to the model. And now the model, the label of the tool actually, so there are two tools, like the word tool in the caption, right? But now the label of the tool will not depend on the context rather than just the entity name itself. Okay, so that's the first type of a shortcut that we hope we can get rid of. And the second one actually is another shortcut we find the model exhibit. So if you recall that clown kicking soccer ball or clown making blue animal example, that's an example where the model just try to treat everything, try to find anything that you mentions in the caption, even if regardless of whether that entity actually appears in the image or not. So this is results from an imperfect unification between the detection and grounding task. So as you recall, a GLIP is trained on two types of data. The first type of data where the prompt is very like artificial, it's just a list of entity names. And the second kind of data we call grounding data is the query is a kind of a caption that always corresponds to the image. So this creates a format shortcut or hallucination. Every time the model sees a caption, it's always aligned to the image. So at test time, whenever you write a caption, write a query in the form of a natural sentence, the model will think, okay, all the entities should appear in the image, and I will just try to detect everything, every entity you mentioned in the caption, whether that actually caption is correct or not. So yeah, so this is the example. Yeah. Whenever you give a caption-like query, the model will always try to find something for you in the image, whether that caption is correct or not. Yeah, even you can even do like crazier ones for the current model. You just write a completely irrelevant thing like a bird flying in the sky, and the model will try to find something look like a bird for you. Yeah. Yeah, so this is more of a like an artifact that created during pre-training where you don't include any negative data. So that design was actually resulted because in object detection, in a traditional detection task, you usually try to keep all the, you don't give it negative queries. You try to always keep your keep all the boxes you can find. But actually in our case, so the solution is very simple. Is now you can try to create some hard negative caption, for example, of a polar bear holding a mallet and versus a toy bear holding a mallet. Now the model should not give prediction for the polar bear in the first sentence, but also importantly, it shouldn't give prediction for the mallet, even if the entity mallet appears in the image. But because the whole caption is wrong, it's not held by a polar bear. So a model should not also give prediction for the mallet in the first caption. So that's very different from like in your usual pre-training, when you don't have this carefully crafted hard negatives. Usually, all you need to do is look at the entity name. Yeah. So now the mallet depends on its language. Label of mallet depends on its context. Yeah. And we also sometimes give full negative query where none of the query matches the image to break that that hallucination problem where the model will always try to detect something for you. Any questions so far for this part?
No,
Okay.
it's very
Yeah. So so combining that two idea together, where the this is like the final algorithm for trying to get what we actually do when generating the queries. So basically the input is you have a picture, you have boxes, and you also have some like here is we're assuming we are generating query from detection data. So in that case, what you get is a list of vocabulary of that detection data set, and you also know what entities appear in the image. And you also have the alignment between those boxes or regions and the positive entities. So yeah, you don't have to read every line, but the key part is two operation. First one is you sometime with a probability, you drop the original entity name from your prompt. And also the second, the last two line operation where you subsample your queries and you reassign your labels. And also and importantly, you allow your queries to be completely negative, not containing any positive entities to break that hallucination. Okay, so that's the that's a master part. So the experiment. So for experiment, I hope any question for the master part.
no.
Okay, so if not, yeah, I'll just jump to the experiment. So the experiment is the original GLIP, and there's another follow-up to GLIP called Fiber, which I won't introduce idea, but it's the same class of models as GLIP. But with much better performance. So they are both trained on detection data, grounding data, and also the pseudo label data I mentioned. So for training our version, we call it DesCo GLIP or Fiber. We don't make any architecture changes, and we initialize from the baseline model. The only difference is the training data or the label assignment part I just showed. We use the same source data as them, but we use GP2 to augment the data and also apply the context sensitivity augmentation we talk about to force the model to read the descriptions. Yeah. So so this is the experiment results we get. So yeah, if you're very familiar with the numbers, you can you can somehow get a sense what the improvement there. but basically on this very challenging LVIS and also the this year's new challenge Omni label, you can see very evident improvement there. And even like for example, our baseline is GLIP tiny. Adding our DesCo training, DesCo GLIP, but still a tiny, like the scale is a tiny model. It can actually outperform the larger model, like the original GLIP large. So that's very good. Yeah, and the same goes for fiber. Once you add that, like original fiber is also very close to the GLIP large model. But now adding that, you see even more evidence jump. And this even outperforms like the newer model, like the grounding dyno, which has a better detector backbone than us. Yeah, and we can see very evident improvement there.
And all these algorithms that you're comparing with are all based on prompt, right? Fiber and.
Oh yeah, yes, yeah. They are like these. I think the GLIP and grounding dyno and the fiber, they are all like the language-based detection models. Yeah. Some models are not fairly comparable, but the like GLIP tiny and the fiber are like directly comparable.
Yep.
Okay. Yeah, so the Bayesian study, I just want to note one thing, is that you can see the drop in the entity name has a very evident effect. So this is a GLIP tiny model. And if you train it without the context sensitive augmentation we do, you don't force the model to read description. You can see there's almost no improvement. But that's, I think, why prior work sometimes doesn't observe much difference, even if you find a way to add descriptions to your pre-training corpus. But now once with that context sensitivity augmentation, you can see a very evident jump in there. Yeah. And we'll also conduct I think it's in this one, like the pre-training task, we also make it as an evaluation task where like you give the model to very confusing queries that have the same general entity type but differs in their description, and you try to ask your model to distinguish them. So very interestingly, GLIP is very insensitive to these context changes. So you can see we calculate like between two predictions, two confusable queries, how much does the model prediction change? So we calculate like how much the box prediction, the coordinates change, and also how much the confidence changes. And you can see the GLIP does like the prediction is almost the same for the two queries. So it doesn't actually base its prediction on the context. Yeah, but for our model, it performs much better under this very challenging test. Yeah. Another interesting experiment we do is you can the detection performance will improve when your language model size grows. So this says that if you give more accurate descriptions, your model will get better performance. So one example is this rollerblade. So rollerblade is like in this image is actually this very tiny thing attached to this person's feet. So it's actually very hard to detect this. So if you give a prompt from GPT Queric, you get a rollerblade, a kind of sports equipment blades that rotate on the ground. So that's actually not correct. But if you give it the Da Vinci one, the model will give you an accurate prediction. Yeah, so we think that's very, very interesting. Yeah. Also shows like potential if you manage to give even more accurate description, because it also supports some errors in the Da Vinci, or more targeted, because sometimes the Da Vinci will just give you more of a quite general and not very specific description that distinguishes this entity from other similar entities. So if you manage to do that, we think there could be further room for improvement. Okay, yeah, so that concludes the experiment part. So the takeaway is, so current models are not, although they already show very strong performance on all those benchmarks, but these benchmarks are mainly designed for entity-based recognition. So as long as you know the entity name, then you're good to go. But now we are moving, I think, to trying to teach the model to handle more complex language queries. And then you have two challenges. First, you don't have enough pre-training data in that similar format. and also your model doesn't necessarily, which is I think a very novel finding here, is that model doesn't always not always use information, even if you provide the description at both training and inference time. So we propose this DesCo description conditioned learning to enable the model to do that. And I think another way to interpret our work is that we are also kind of using language descriptions as a supervision signal. Okay. And this actually traces back to the very classical idea of like trying to decompose the task of recognizing animals like here into more about identifying the individual attributes of these species and then putting them together to actually know which category they are in. Yeah, so if you go take a look at the bigger picture of how our supervision sources changes over the years. So before, a few years ago, we usually use labels as your supervision. So you have this very classical data sets of ImageNet or COCO, but usually they are quite costly to annotate, right? So, and you also only have very limited vocabularies. But now with the surge of these vision language models, you have now use your image caption data as your supervision. So for like CLIP, Align, View, CLIP, those style of model. So the good thing is that it's easy to scale. But as we showed that this kind of a coarse supervision only mainly just your model will learns mostly object entity alignment. So in our work, we actually explore the description as a kind of supervision. So still, it's very scalable as the image caption data, and you don't need additional human annotation. You just ask the GPT to rewrite the text part of your pre-training data, and you are somehow decomposing the task of object recognition into a grounding of their attributes, parts, shapes, etc. So, but we don't do a very explicit splitting between in the description, like this part is the attribute, this part is about the parts, this part is about the shapes. We just ask the GPT to write whatever it thinks is most relevant. So, and now you can support more flexible language queries. Yeah, and we think this more and more future work will try to discuss whether we can use not just a raw image caption, but more about this descriptive language as a kind of a supervision signal for more generalizable computer vision models. Yeah, and with that, I will conclude my talk. Okay. Any questions?
Yeah, super interesting work. While I have been listening about the success of prompts and prompt learning everywhere. I know I personally did not explore how the descriptions or how rich or well populated they are make so much of a difference when comparing results with clip-based model. I have a few questions, and meanwhile, if anyone has a question, feel free to drop in the comments in the chat or raise your hand so that I can give you permission to turn on your mic and you can talk as well. Right. So looking at the success of clip-based models compared to the one with no clip, do you think it comes with any kind of drawback? Clip models somewhere that they fail, somewhere that they won't work, or one should be reluctant to use them everywhere?
Oh, you mean because we now observe some drawbacks of the clip, which what should we do? Yeah, I think that overall, if your goal is still trying to mostly do object entity alignment, because that's actually most benchmarks, actually what benchmarks test. So if you are mostly interested in that, I think clip is still very good option. But if you are really looking for those very hard tests I just showed, where you're really trying to use your language for very fine-grained control of what you get, then yeah, clip and even GLIP, these type of model are not very good on that front. Yeah.
Makes sense. And so another question would be, because this was a part of a challenge, as you said, how different is it to conduct research for a challenge and then write a paper compared to writing a paper for a PhD?
I think this actually is more of a coincidence that when we had the idea before we know of the challenge, and we were in the middle of developing that. So so our original like benchmark was just the LVIS. But once we got some initial results, we actually got an email from the organizer of OmniLabel say, okay, we have this challenge, and we say, okay, this actually fits our mission. So we just apply our method there. So it's really, I think, kind of a coincidence. But I also think it also shows that like sometimes if you're just trying to optimize for a challenge, then you may not like the idea sometimes you get the inspiration or idea from a challenge, but you also have to develop your novel method there. If you're only optimizing, just thinking how can I get better performance there, you may not actually get what you want. Yeah, so like we're more like developing our idea, and coincidentally actually solve the challenge pretty well. Yeah, rather than we want to get better performance on the challenge. Now we have to think about our method. Yeah.
Interesting. And because there are multiple concepts involved at the same time, maybe like prompts or contrastive learning as well, and then usage of ChatGPT. I have another question for ChatGPT though. How computationally expensive do you think it is?
For ChatGPT?
No, for like using multiple concepts such as prompt as well as contrastive learning, everything together.
Oh, I see. Oh, sorry, I didn't get the question. So do you mean like if we trying to do this kind of a contrastive learning, does it add additional computational cost?
Yeah, does it add additional computational overhead, and like how well do you judge your method when it comes to to the computational complexity?
Oh, I see. Yeah, that's a very good question. So yeah, that's actually a very good question. So one thing you might notice is that before you are only querying the model with like an entity name, like say you just mallet, bear, etc. So but now you actually, for each entity, you actually get a long sentence describing what it is. So that brings a lot of new computational overhead. Like say like in the current, I actually have a more advanced implementation, but talk about that. But in the current implementation, what you do is your like the number of words you can fit in a prompt is fixed. Right? Like even like with ChatGPT, fitting more word tokens will cost you more money. Same in our model, like you usually have a more of a fixed budget for how many words you can put in a prompt. So if you only put entity words, then you can fit like hundreds of those easily. But now if every entity name becomes a long sentence, then you naturally fit less. So that actually reduces somehow the training efficiency and also the inference efficiency. Yeah, but I also but then also we have a more advanced version where you just don't put them into a long paragraph like this. It's more about you encode each long description with a language encoder, but you only take out one sentence vector out from it. And then you compose several sentence vectors representing each entity together into a paragraph of vectors, and then feed it to the final vision language model. And that will greatly reduces your computational budget cost. I'm not sure if I answered your question.
You do. Just another question out of curiosity. What machines were you using for this?
Oh, I see. We used about 8 like we didn't use 8. It's more about like 4 A6000 GPUs. Yeah, because more of a fine tuning rather than very heavy pre-training. Yeah.
Makes sense. Great. That is all that I could think of, and I don't see a question in chat. But yeah, the presentation with all the examples was very gluing. I wasn't distracted even for a minute. It was very interesting presentation with all the results. Thank you on that. One question, which is not related to the paper. You mentioned that you have a research scholarship from Amazon as well. And at some point, I do get emails from PhD students that want to know more about just publishing paper for PhDs, like, for example, internship and scholarship from different tech giants. So that could be another series, but yeah, just to ask, like, how does it work usually? Do you have to conduct research on a certain subject that the particular funding agency is interested in, or do you have to intern with Amazon? Like, how does it work?
Oh, I think that fellowship I got is more from because the department happens to have a collaboration with Amazon. I don't have very specific advice on that because I think I'm quite lucky. So yeah, but I guess the general advice is somehow you keep doing good research, and there's always a way to connect your research to like certain funding projects, whether you are like developing technique for unrelated area, but later you can find, okay, actually it works for that funding project I have, or like even you do very good research, new funding project will come along, like as long as you do very good research. Yeah. So, but I guess I'm quite lucky on that front. So.
I see. How long have you been working on this particular area? Like using descriptions for image?
Oh yeah. So like GLIP was when I was interning at Microsoft. So there's doing So that's like the first time we try to use a language to solve this object detection task in computer vision. And then later, and when I'm back at school, we were said, okay, can we actually can we enable this model to do more than entity-based recognition? So that's how this project somehow got started. Yeah. So like generally, I have been working on more about vision language pre-training. So basically, you have like after BERT, you see the power of pre-training a lot of text corpora. So in vision language, you also get a lot of vision language data. So our first work was visual BERT, which is showing, okay, you have a lot of vision caption data. You can use that to improve your performance on vision language tasks, such as visual question entry. But later, people find, okay, you can also use that data for very classical computer vision tasks like image classification. Yeah, so that's somehow the trajectory I was moving along. Yeah.
Yeah, interesting, super interesting. Great. So yeah, these were the questions from my end. Thank you for joining us and giving us your time.
Yeah, thank you for hosting the talk. Yeah, and raising great questions.
It's been pretty long since I hosted a talk. I was occupied with my PhD exams, but now I'm planning on getting back and hosting at least 2 talks a month. So thanks for the audience for being patient and even showing up after such a long gap. And yeah, Harold, we hope to see even more interesting work from you in future.
Thank you very much. And thank you for hosting this series. Yeah. Thank you for all the audience for attending. Yeah.
Thank you. Okay. Have a great weekend, everyone.